Okay, our second of 4 videos working on most of the practice test problems. So if you could flip over and find problem 19, it is firmly in chapter 2. This is one of our simpler ones. So you have an airplane, increasing speed, at a rate, so increasing velocity at rate. This means it's accelerating at 15 meters per second squared. I need the time to go 100 meters per second to 160 meters per second. Again, really straightforward problem. So what is acceleration? It is a change in velocity over change in time. And that's simply, so we're asking the time it takes. So I'm going to be solving for delta t here. Okay, so you can multiply both sides by time and divide both sides by acceleration. But what you get, when we get to that algebra, please make sure you can do this, is delta v over acceleration, which is v final minus v initial over acceleration. So 160 meters per second minus 100 meters per second over that acceleration of 15 meters per second squared. And I find out that it takes what? Pause me here, do the problem yourself. I only can use 1 sig fig because I have only 1 sig fig there, so it takes 4 seconds. Again, pretty simple problem, probably something too simple to put on the final, but it could be a part of something else. If we look at 18 is one of those fun ones. Looking at vectors, this is the beginning of the chapter 3. Look at these slides if you're confused, but this is vector A, and then I'm told that this is vector B. Okay, and then it wants negative 2a minus b. So always give it a name. I'm going to call it C. C is negative 2a minus b. I need to draw it out. So pause me and you try to do it yourself. But again, I'm going to keep going so that the videos stay short. 1a, I'll make 2a and then reverse it. So I would have negative 2a like that. It's 2 lengths of a in the opposite direction, so the negative does. Here's b, so this would be negative b. And if I want to know what c is, I start from where I started from, and I draw a line. My professor used a dotted line, and this is the answer. This is the resultant vector, negative 2a minus b. Okay, so just drawing that and that is not the answer. This piece here, this dotted vector, that is the answer. If you're struggling with this, again, go back to those chapter 3 slides. I go over these in detail and I gave you tons of examples. And in that slide deck are a bunch of quick checks. So you can pull up a slide, check yourself, and go from there. Okay, take a minute, flip over and find 6. Little bit of a weird one here. Okay, so I'm told I've got some components and I want the vector difference. Vector difference. And I'm given this information. Okay, vector difference. What is a vector difference? Well, they actually write vector difference of b minus a. So again, anytime you're doing vector stuff, give it a new name. So I'm going to say I'm going to find c equals b minus a. Okay, I can't mix up x and y information. I just separate x information from y information. So therefore, I'm going to write c sub x equals b sub x minus a sub x. And c sub y equals b sub y minus a sub y. Actually, you know what? I'm going to do these vertically. So let me just scoot this. I'll put it over here. C sub y equals b sub y minus a sub y. Now, what is the big kicker with this? Watch the signs. Oop, getting in the way of myself. Sorry about that. Watch the signs. Okay. B sub x is negative 5.1. Don't forget that. So c sub x equals negative 5.1 minus a sub x, which is 7.6. So c sub x equals negative 12.7. C sub y is b sub y, which is negative 6.8 minus a negative 9.2. So I'm actually going to add that. So c sub y, c sub y ends up being 2.4. Now, this is not the answer. I need the vector c. So there's two things I'm actually going to do. And I'm actually going to ask you in this example for a little bit more than what the problem actually says. The problem says, I'd like to know the resultant vector. But let's actually draw it out. If this is an xy axis, so this c sub x is right here. That is negative 12.7. So, c sub y is very small. So let's say that's right there. C sub y is right there. That's 2.4 positive. It's a negative x, positive y, yes. Okay, so I could actually also get, if this is my resultant vector c, I can get the magnitude and this angle. Let's get the magnitude first. We'll just use the Pythagorean theorem. C equals square root of cx squared plus cy squared. So c equals square root of 12.7 squared plus 2.4 squared. Use just the magnitude. You don't need the sign here. So c is about 12 meter, or I'm sorry, I don't think I put units. Okay, c is 12. Okay, make sure you can get that, square that, add it to that, take the square root. So it's 12, but where is the 12? 12 isn't very helpful. I need to know where 12 is. So I need this angle right here, theta. Well, I can use any trigonometric relationship because I now know that c is 12. I know that c sub y is 2.4, and cx is 12.7. So I could do tangent between these two, sine between these two, cosine here. But the first things I found were these two. So I'm going to stick with those. So I'm going to say tan theta is opposite over adjacent. Theta equals opposite over adjacent, inverse tangent. Okay, so theta is, the opposite is, here's my angle. So the opposite is c sub y. I'll write that out, sorry. C sub y, which is c sub y over c sub x. Okay, which is 2.4 over 12.7 tangent inverse, and I get a theta of, I think it's 17 degrees. I did not do this part on the key. Anyway, whatever degrees you get, I believe it is 11 degrees. I think that's 11 degrees. Yeah. Now, here is a weird question. That 11 degrees is here. So if I'd drawn this and gotten 11, and I said, here's my answer, I've boxed my answer, and this is where it's located, that's actually correct. But what if I said with respect to the positive x-axis, WRT, with respect to the positive x-axis, I'm asking for this angle. Let's just call it angle. Okay, if I wanted angle, how many degrees is it from here to where the vector is actually located? I would need to do what? That's 90 and 90, so that's 180. 180 minus 11 is 169 degrees. And so that is what this would be. Excuse me. Okay. And then let's do one more. We're going to grab 21. Okay, for 21, bowling ball weighs on Earth, so I have weight on Earth is 100 newtons. Okay, same object, weight on planet X. So I'm told gravity on X is equal to 14.8 meters per second squared. So what is weight on X? Question mark. Well, if weight equals mass times gravity, then weight on the Earth equals mass times gravity on the Earth. Mass doesn't change. Mass stays same. So let's deal with Earth here. I know the weight on Earth. Well, it wasn't given in the problem, but I had to memorize gravity on Earth because Dr. Urban said I did. Okay, so I get the mass from this side. Mass equals weight Earth over gravity Earth, which equals 100 divided by 9.8, or 10.2 kilograms. This is just the mass. This is not the answer. Now over here, I want to know the weight in planet X. Well, that would be that would be mass times gravity on X. Mass times gravity on X. So I just take this mass, plug it in here. So weight X equals the mass, which is 10.2 kilograms, times the gravity on X, which is given in the problem as 14.8 meters per second squared. Am I still fitting? I think so. So the weight on X is how many newtons? Now, the number you're going to get is actually 151 newtons. But in the problem, I'm only given one sig fig. Now remember, on an assessment, I won't do this to you. But if that were actually how the problem was set up, then the proper answer would be 200 newtons to give me one sig fig. Okay, stay tuned for the next round or open up the next video.